This video focuses mostly on the parameter bail thresh. That is, when should PyNita really run at all, or when should it just bail out and model the pixel history just using a single segment. So it's kind of an important one and has some diagnostic tools, i.e. images that are associated with it. So it's worth spending a little time exploring. So I will open up the PyNita binary, and we'll just go grab the demo data set. So if you might want to start with the basics video before you get to this, if you're not familiar with any of this, because I'm going to cruise through it. So I'm going to load up my files, set my working directory, submit, grab a user configuration file, just leave it unchanged for right now. Grab the oil palm sample points from the demo data set. Okay. And okay, before we run this, now we're going to step back and look at the parameters. So we're going to leave mostly the parameter set alone for right now, but we're going to look at this bail thresh. And so you can see that there's a nice tooltip associated with this and all of the other parameters that you get to set. But the basic idea is that if you set this very high, Nita is always going to bail out. So it's just not even going to bother building up multiple segments. And the advantage of this is that you can get a first look at the trends in your data in a much less computationally expensive way. So let's just start out by setting a high bail thresh and save this. And let's look at a few points. So for these 9 points, you can immediately see that there's only one segment. It's not quite a simple linear fit in the statistical sense, but it's a single segment fit from the early points to the end points. Okay, maybe not the best way to model some of these pixels that clearly have disturbance, but you may not know that in advance. And so the power of this really comes in looking at a full image stack because you can process it so quickly. So let's just proceed there and open up the demo input stack, which is where? So I got my NBR stack, and let's create a subset just for even faster processing, but a pretty big one. Throw all my workers at it. This shouldn't take long at all. So we finished processing, and now we can go to step 4. And okay, so many of these disturbance-based metrics are not going to be useful at this point because we haven't modeled any disturbances. But these bottom 3 are going to be useful diagnostics because they run regardless of how many segments that you produce. So let's start with linear error. So linear error is just essentially the deviation of your actual data points per pixel from a simple linear fit. And so you can see where linear error is low, that either means that it means both noise is low and also your data may be well modeled by a single linear fit. So for instance, there may not be a disturbance. So if I click here, you can see that that's pretty much true. This is intact forest. While there's always going to be some noise, it's pretty clearly stable and modeled well by this one line. By contrast, if I click over here, you can see that the noise is fairly similar, but it's clearly a nonlinear process. So this particular pixel would be best fit by 1 to at least 3 segments to characterize the nonlinear disturbance and recovery process. Just another example. There's going to be kind of middling examples as well, and that's where things get a little more interesting. But in this case, they're generally fairly obvious. Like this is clearly requires more than a single line. All right, so that's linear error. You can also look at noise in the data, and this is a fairly not noisy data set, so there's perhaps not too much to see. So low noise is going to be there compared to high noise, and the noise is the actual presence of a disturbance is not really considered noise, because the noise is just measured as the forward finite difference. So basically the difference between consecutive points. And finally, the Bale cut. This is going to be the number that actually plays into what you want to use as your Bale thresh. And so clicking on a pixel, what did I just click on? I can hover over it. I can see that in the bottom right corner of that window, you can see that there's a value of 2.7. This means that NIDA is going to run up until a Bale threshold of 2.71. Over here, you can see that we've got a 0.96. So in order to get NIDA to actually run, you'd need to set the Bale threshold quite a bit lower. So the lower you set that Bale threshold, the more pixels that on which NIDA is going to run. And so in this case, you probably wouldn't need it to run on this pixel. So you may want to set, somewhere between 1 and 3 is already looking like maybe an appropriate range. So let's try some of these middling pixels. We got a 2.2 there that you certainly want to run. Let's see, something like that is, oops, I forgot which one that was. I think it was like right there, 1.85. So I usually start with just running something like 1, because even if NIDA runs unnecessarily on some pixels, it doesn't necessarily lead to a bad result. It just leads to a more computationally expensive process. So if I change this from 10 to 1, save this off, and let's see, we'll keep the same subset. Go ahead and run that. And we waited about 10, 15 seconds there for those. It took a little longer than before, but we got some image metrics. And let's go see. So nothing is going to change in these figures down here, because again, they're only based on that initial linear fit. But now we can start to actually get information about disturbance. So we picked up a lot of the disturbance in the disturbed part, and we still modeled. So some of these with that fairly low Bale thresh, we did run NIDA, probably unnecessarily. Who knows? Maybe necessary, maybe not, probably not. So we might be able to bump up that threshold to 1.5 or something like that if we wanted to be a little more parsimonious with these fits. Got that pretty well. And this is without even touching any of the other, we didn't touch any of the other parameters yet, so we could do a better job with these fits as well. But so that's the basic idea, is that Bale cut image gives you an idea of the range of values that may be appropriate for your Bale threshold.